Yes, so let me start, because I have to run off at the very end, so I might sort of forget or sort of get distracted. So let me start by thanking Somnath and Ritvik for organizing this wonderful workshop. So I really enjoyed my stay here, and yeah, so thank you for that. And so today I finally get to the actual topic of my lecture series, so symplectic homology or cohomology. And so there's what so I'm almost a convert now. So there's been this debate sort of in symplectic homology. There's sort of there are two groups of people. One so the same object by some people is called symplectic homology and by others symplectic cohomology. And I'm close to converting to the symplectic cohomology, but I'm not quite there yet. So I'm going to call it symplectic homology today. But it's sort of, when you read Seidel's paper, what he calls symplectic cohomology is what I would call symplectic homology. And so I gave you a bunch of papers where if you want to have some background reading. So this one I already mentioned in my first talk. So Abondandolo Schlenk also have a short section on symplectic homology and some applications of that. Then this Seidel paper was quite influential, so that is maybe 10, 12 years old, and it still sort of contains, this is a very sort of useful survey if you want to see sort of the basic stuff. And then if you want to get more details, you can look at Mohammed's sort of substantial sort of it's almost a monograph. It's part of a book that Alex Wansha and I edited, where he discusses symplectic cohomology and Viterbo's theorem, which is the thing about symplectic cohomology of cotangent bundles and an isomorphism to the homology of the free loop space. But so when you read his thing, he only talks about cotangent bundles, but in fact all his constructions work quite generally. So if you just replace the cotangent bundle by a general Liouville domain with C1 equals 0, say, then his constructions still go through. So recall our setup is that we have omega lambda is a Liouville domain. So that means lambda is a one form, which a d lambda is a symplectic form. Omega has boundary. So the boundary of omega I'm going to denote by V, and I'm going to denote by alpha. That's going to be the restriction of lambda to V. So that's going to be a contact form on V. And basically I want to do Floer theory on this thing. And one other thing we talked about yesterday was the completion of W. So W was like this compact thing with boundary, and then the completion, we just added this half-infinite cylinder. All right, so this was like, so this is W, and then this was this kind of half-infinite cylinder with lambda on this part is of the form rho times alpha, where alpha is pulled back from V. And so now we want to do Floer theory on this kind of thing. And now the first thing you notice when you play around with examples is that now, in contrast to the closed case, your Floer homology will really heavily depend on what kind of Hamiltonian function you use. So naively, the first thing you might try is you might look at compactly supported Hamiltonians. So then you have to, then of course you have many fixed points of the Hamiltonian flow, but if you forget those and only look at the others, then you get some well-defined theory, but it's fairly boring. It basically gives you the homology of your domain relative to its boundary. So that up to some degree shift. So that's not terribly interesting. So I mentioned yesterday at the end of my talk, sort of in the kinds of questions one wants to think about, is that one thing that one's really interested in is to sort of bring in the rate flow of this contact form on V. Right? So the one thing one wants to study maybe with these tools is the rate flow of V, so of this contact form alpha. And so for that, you need to somehow bring in these rate orbits, the periodic orbits of the contact form alpha. So let's call P of V and alpha are the periodic orbits of the rate vector field. And so, and I'll allow, once I have one, I can also traverse it several times, so that will be different orbits for me. And then we can look at the action spectrum of V and alpha. Those are going to be all the real numbers of the form integral over gamma of alpha, where gamma is one of these periodic orbits. This is called the action spectrum. And it's basically, note that sort of the rate vector field has a property that inserting it into alpha gives 1. So this is just sort of, this integral just measures the time it takes for a periodic orbit to close up. Right? So this is just sort of the period of the periodic orbit that we're recording here. And the fact is that this is a nowhere dense subset. Right? These are all positive, right? And this is nowhere dense and bounded away from 0. And yeah, so this is what we need to know. And so to motivate what kind of Hamiltonians we look at here, let's look at Hamiltonians in the symplectizations. So yeah. No, it could be empty, but it's also nowhere dense, right? Okay. So, I mean, somehow the goal, I mean, the Weinstein conjecture says that on any closed manifold, you have at least one closed periodic orbit. So if the Weinstein conjecture were true, which is known to be true in dimension 3, but not in higher dimensions, then this would always be a non-empty set. And then, but even if it's empty, it's still nowhere dense. So, but I mean, it's generally believed to be true that it's non-empty, I would say. Right? Do you agree? Right. So, I mean, in fact, so the Weinstein, while we're at it, the Weinstein conjecture sort of claims the existence of one periodic orbit. Experience tells us that, except for very special examples, there are always infinitely many in things, in examples where we can actually sort of understand all of them. So one might try and make more ambitious conjectures about sort of making some statement about what the exceptional cases might look like, and then say in all other cases there are infinitely many. But this is far beyond what I'm going to talk about today. All right. So we considered our symplectization with, so I'm going to call the coordinate rho here, and then I have the symplectic form is rho times alpha, where alpha is my contact form. And now on this, I can look at, this is a perfectly nice symplectic manifold, so I can look at Hamiltonian dynamics on this, and I'm going to look at a Hamiltonian function of a very special form, namely it only depends on the first coordinate. So it's just little h of rho for some function on the positive real numbers. So these are very special Hamiltonians, and now the exercise is that for such Hamiltonians, the Hamiltonian vector field is actually given by the derivative of H times the ray vector field. Right? So I'm on my cylinder. I have a cross section I'm on my cylindrical symplectic manifold. I'm in my symplectization. My cross section is V, and so when I'm at height rho, then the Hamiltonian vector field is a rescaling of the ray vector field by H prime at rho. And so we see that if you're looking for one periodic orbit, we're going to have so one periodic orbit appears on level 8, rho. So meaning sort of I have here, so here I have like 1 times V, and here I have sort of a general rho times V. So level rho, I mean sort of rho times V. So on a one periodic orbit appears on such a level if H prime of rho is one of these periods. So if H prime of rho is in the action spectrum. Right? And so basically, if I want to see more and more of these periodic orbits, or somehow if I want to take into account my periodic orbits, one approach would be to look at Hamiltonian functions on the completion, where on this cylindrical end, my Hamiltonian just depends on the rho coordinate, maybe up to some small time-dependent perturbation to make things non-degenerate. Right? So notice that once, maybe I should have said this. Once, if you're looking at this H, which is independent of time, then if we have one periodic orbit, then of course we have a whole one-parameter family, because the whole rape orbit, we can rotate that, and there will still be a one periodic, because we haven't broken the time symmetry. Right? But if you take a small time perturbation of this, then actually each one of these rape orbits breaks up into 2 Hamiltonian orbits. Well, let's not worry about that too much. So one way to sort of incorporate all these rape orbits into the picture would be to take a Hamiltonian on the completion which is essentially of this form up to a small time-dependent perturbation, where H prime goes to infinity as rho goes to infinity. Right? Then I'll see all of them somehow. Maybe I should also require that in the interior, sort of near this boundary, H prime should be 0 or close to 0. So then I would really see all of them in my chain complex. But we'll actually do something slightly different. So we're going to look at so we're going to stay on W, and we're going to look at, recall that sort of not only did I have this positive half of a symplectization outside, I also had sort of the negative half of the symplectization sort of extend to the inside here. And so I can pick some color neighborhood here, which looks 1 minus epsilon 1 times V, right? And lambda is still rho times alpha. So if I choose the flow of my Liouville vector field with negative time, I can sort of get a neighborhood. I can get coordinates on a neighborhood of this boundary, which look where things look in this way. And so on W, we consider Hamiltonians now. To R, such that on some color of the boundary of W, H is of the form A rho plus B for A, let's say, non-negative, B in any real number, and A not in the action spectrum. Right? And so the slope of such a Hamiltonian, which is A, is not in the action spectrum, so that means that in that color neighborhood, I don't have any periodic orbits. Right? Because this computation says that for Hamiltonian of this form, periodic orbits, one periodic orbits only happen at levels where H prime is in the action spectrum, but I arranged that H prime is not in the action spectrum. So no one periodic orbits, I should say, right? Okay. I'm sorry? Actually, this is if and only if. So for if my H is really independent, it really just depends on this coordinate, then it's if and only if. Yes. All right. So we found a class of Hamiltonians, so that at least sort of the periodic orbits stay away from the boundary, so they stay in the interior of my compact domain. So that's already nice. And now, to do Floer theory, I also have to make sure that my Floer cylinders stay away from the boundary. So if I start touching the boundary, I get into all kinds of issues with compactness. So in order for Floer cylinders to stay away from V, which is the boundary of W, we need to pick J of a special form and my choice is that, again, in this neighborhood, so on this color, J should be, well, J should take the kernel of alpha to itself, and J should take rho d rho, so this Liouville vector field, it should take that to the wave vector field of alpha. And if we require this, then it turns out that now not only do we not have any periodic orbits near the boundary, but also any Floer cylinder connecting two periodic orbits will not enter this neighborhood. So that there's a maximum principle ensuring that no Floer cylinder, so a Floer cylinder for me is really a finite energy solution of Floer's equation, that no Floer cylinder enters this color. So once we know these two ingredients, then we're really in business, because now observe that our symplectic form is exact now, right? Omega is d lambda. So since omega is d lambda, we have our favorite assumption that omega vanishes on pi 2. Right? Because if I have a two-sphere and I integrate d of something over it, then it's the same as integrating that something over the boundary, which is empty, so it's 0. That's Stokes' theorem. And so we get L infinity bounds on the derivative of u for any Floer cylinder right, that was the bubbling analysis that I did. And so once we have that, and we know that all the Floer cylinders stay away from the boundary, then we get the usual compactness thing that we know and love. And then, so you get a well-defined Floer boundary operator, or Floer complex. So this is now going to be CF, again, will depend on H and J with the boundary operator, I guess, which also depends on H and J. Yes? Sure. So we're looking at solutions of the Floer equation. And so they're solutions to a PDE, so when you look at, I mean, the way I've set things up, so I don't really have time to do the calculation, but there's, I mean, you know that on C, let's say, harmonic functions don't have an interior local maximum, and this is the same kind of result. So basically, if you look at the function rho restricted to a Floer cylinder that might enter this region, that would be a subharmonic function, and then that wouldn't be allowed to have a maximum. That's basically the reason. So, and then there's also an integrated version of that. So if you really sort of, I find the integrated version even nicer. So you should look in Mohammed's work. So there, I think it's chapter 9, and then so these are chapters of our book. So chapter 9 is the first chapter in his thing, and then chapter 9, section 6, I think he discusses this maximum, so this integrated maximum principle. No, they have to stay away. So the point is, so my picture is now the following. I have my Liouville domain, and I have this color where I have this condition, and my H is of this special form, of this form. And these two conditions together ensure, well, first, the condition in H ensures that any periodic orbit that I might have stays away from this part. And then the condition on J, in addition, ensures that also Floer cylinders have to stay away from this part. So they never ever go there at all. They cannot enter there. They're forbidden from entering this region. And that's what gives me compactness. Okay, so then I get a Floer homology of H and J. And now the sad part of the story is that's still not an invariant of my manifold because it heavily depends on my choice of H. Right? So the problem, if you want to call it that, is this still depends on H. And the way it depends is essentially through this slope here. So the point is, if you try, so what was our argument for independence? We tried to construct, we constructed continuation maps, and then so we composed them and showed that they all had to be isomorphisms and so on. So now when you try to implement that same program here, so in the present setting, if you want to have a well-defined if you want to get a well-defined continuation map, from the Floer complex of H plus to the Floer complex of H minus J minus, then in order to have a similar kind of maximum principle which ensures this compactness, we need that the slope of H minus should be at least the slope of H plus. So if when we, right, I mean, so we for the continuation map, we had this Fleur equation where now we also had this S dependence. And when you look at this maximum principle for these kinds of things, in order for that to work, you need a sign for the S derivative. And the way I've set things up, this sign should be non-positive, right? So as S increases, the slope should decrease. And once you have that, then you do get this maximum principle, so you get a well-defined continuation map. So if the slope of H minus is bigger than or equal to the slope of H plus, we do get well-defined continuation maps from the Fleur complex of H plus J plus to the Fleur complex of H minus J minus, and their chain maps and so on. And in particular, as a consequence, we get that for Hamiltonians which have the same slope at infinity, or at the boundary, I don't have infinity now, for Hamiltonians which have the same slope at the boundary, I get isomorphic Fleur homologies. Right, so because for them I can have continuation maps both ways, and I can have my usual argument to show that there are isomorphisms. Okay, very good. So these Fleur homologies only depend on the slope at the boundary, and so now to define symplectic homology, well, we just resort to the only way out that we have. We just take the direct limit. So if you want to produce something independent from a directed system like this, then we can just take the direct limit, right? So the symplectic homology of W and lambda, by definition, is the direct limit over the slopes of the Fleur homologies of the various Hamiltonians with different slopes. Right, so that's the definition. Yeah, I just realized I forgot to mention something. So in the story on closed manifolds, I was looking just at contractible loops. Now I'm looking at all loops, and that's okay because my action functional So in the exact case, so when omega is equal d lambda, AH can be written as the integral over lambda minus the integral from 0 to 1 over h of t and gamma of t dt. And now this makes sense for any loop, right? So I don't need to choose a capping disk or anything like that. So this is well defined because my symplectic form is exact. This is actually well defined on the whole loop space. So this symplectic homology has many different properties. So for example, it comes with as a direct sum over 3 homotopy classes, right? Because my boundary operator is given cylinders. So if two things are related by a boundary, but if the boundary map relates to generators, then they're actually freely homotopic. So I can grade my symplectic homology. So Remark, so SH splits as a direct sum over 3 homotopy classes of loops, and now all homotopy classes are allowed. And yes, so let me see. Did I forget anything important? Right, so here are some more remarks. So as I said in the beginning, if you're interested in only one specific Liouville domain and you just want to study it, then it might be so if you focus on a single Liouville domain, W lambda, it might be more convenient to use a definition of Floer homology, or of symplectic homology, in terms of a single Hamiltonian H. Now on the completion, which H on the end is again of the form H of rho plus some small time-dependent perturbation with H double prime non-negative and H prime going to infinity as rho going to infinity. Right, so that's for example what Abondandolo and Schwarz do. In the cotangent model case, or also Salomon-Weber. So that's slightly different from this direct limit. You only have one Hamiltonian. The drawback is that this is not very well suited for example, for a problem of studying embeddings of one Liouville domains into another. So I'm going to state some result in a little while that says that if you have a Liouville embedding, then you get a map. That kind of thing you couldn't, it's very hard to prove with this kind of setup. So, oh, yeah, then the next remark is that if my slope is very small, so smaller than the minimal period of a Rabe orbit, so I have A bigger than 0, but less than the minimum of the action spectrum, then I don't have any generators coming from the boundary, right? Because they only appear when my slope sort of is bigger than that period. And so for such slopes, the Hamiltonian Floer homology of the corresponding H is just isomorphic to the relative homology of W relative to its boundary. And so since I'm looking at the direct limit, I have a natural map into it from any one of these things. So in particular, that says that I have a natural map from the homology of W relative to its boundary into our symplectic homology. And now, if we knew that this is not an isomorphism, then we could conclude that there had to be at some point, something here has to get killed or something has to be added. So that means there must be some Rabe orbits, because these are the only ones the only other things that appear when I increase the slope. So if this is not an isomorphism, then we know that V, the boundary of W, with its given contact form alpha, must have periodic Rabe orbits. Right, so this was one of the motivations for Viterbo to study this kind of homology, because he wanted to say, well, if your contact manifold is the boundary of some exact thing, if it's the boundary of a Liouville domain, then actually it satisfies the Wittgenstein conjecture. Right? And you need this extra assumption that this map is sort of not an isomorphism, but in many cases you can prove that. And so let's do a computation, right? So throughout my talks, I've always had this running example of C or the two-ball. So let's do the computation of symplectic homology for the two-ball. Right, so for the ball, well, what's my contact form? My contact form is lambda is 1/2 x dy minus y dx. So restricted to the boundary, that sort of has the same formula. So my Rabe vector field of the contact form alpha will be twice x dy minus y dx, right? Because then that inserted into here gives x squared plus y squared. So on the circle, that's 1, right? And so the action spectrum of S1, which is the boundary with this contact form alpha, which is lambda restricted to the boundary, is just k pi, where k is some natural number, right? And so now it turns out that if I look at the Hamiltonian functions, h of z, which are defined as a times norm of z squared, these are linear in my sense. The reason is that this function rho on the symplectization that we talked about in this particular case is really r squared of the, where r is the usual radius. Right, so when r is the usual radius function on C, then it turns out that in my conventions, my rho that I use for my symplectization is really r squared. So this is just of the form a times rho. So this is clearly linear. And so now we can also understand the Hamiltonian flow of this, right? So xh we said was just a times the ray vector field, well, not just on the boundary, but in this case, it's actually the same formula makes sense on all of C, and it's true that xh is sort of, let me just write it this way, xh is 2a times x dy minus y dx globally, and so this is just 2a d phi, right? This is sort of the vector field that turns. And so the flow of this vector field is actually linear, right? It's just rotations with constant speed. And the speed is 2a. So if a is not a multiple of pi, then the fixed point at zero, so note this has a fixed point at 0, right? So 0 is a critical point of this function. So at 0, the Hamiltonian vector field vanishes, and that's a fixed point for all of these functions. And if a is not a multiple of pi, then actually that's the only one periodic orbit. So if a is not a multiple of pi, then then 0 is the only one periodic orbit. And now, since we know the flow is linear, we also know the linearization, it's just the flow itself. And so for a between k pi and k plus 1 pi, this periodic orbit has Condensation index 2k plus 1. Right? So since I said Floer homology exists, we only have one generator. So then we see that Floer homology of Hj is equal to just one copy of Z, and this copy of Z is in degree 2k, because I shift, so to get my grading, I shifted the condensation index by half the dimension, so half the dimension here is 1. So this Z lands in degree 2k if A satisfies these inequalities. If k times pi is less than A is less than k plus 1 times pi. right? And so this tells us two things. Well, it gives us an explicit example where we see that the Floer homology really does depend on H very heavily, right? Because, I mean, it looks the same, but it's sort of, this Z lives in completely different degrees depending on the slope. And also, now, continuation maps must preserve degree. And so, if I have continuation maps between graded modules that live in different degrees than these, but the continuation map is of degree 0, then it only has one choice, it has to be 0, right? So that tells me is that so all these elements that appear at any given finite slope, they have to die at some higher slope, at all higher slopes. So if once I pass another multiple of pi, then this generator dies and some other one appears, but then that dies one later and so on. So all these elements are mapped to 0 in higher slopes. And so the conclusion is that the symplectic homology of the ball vanishes. Right, this was the direct limit over slopes. This is 0. Because all my continuation maps are 0. Because you have nowhere to go in their degrees. Okay, very good. So, in fact, now I can state a slightly more general fact. So it was proven by Kite-Silibak first that if you start with a Weinstein domain and you attach a subcritical handle, so not one of the middle dimension, but smaller dimension. So in Weinstein domains, subcritical handle attachment does not change symplectic homology. So we find that all subcritical Weinstein domains also have symplectic homology equal to 0 because we can get them from a, so this result also holds for higher dimensional balls by essentially the same argument. So all subcritical Weinstein domains have vanishing symplectic homology. Well, on the one hand, that's kind of disappointing because I mean we went through this whole complicated process to define 0 in a very complicated way, but it's actually sort of, if you look at this remark, it's actually good news because if this is 0, this is typically non-zero. I mean, it's always non-zero, so that means that map is not an isomorphism. So for all boundaries of subcritical Weinstein domains, the Weinstein conjecture is true. Every such boundary has at least one periodic Rabe orbit. Right? Oh, so I mentioned last time, I didn't really talk about it, but I mentioned last time that, so a Weinstein domain was one of these things where the Liouville vector field is gradient-like for a function. And let's assume this function is Morse, then it has sort of, and because we're talking about compact things and it has finitely many critical points, and manifold is obtained from the ball, which sort of corresponds to the neighborhood of a minimum, by successively attaching cells of dimension sort of corresponding to the Morse indices of these critical points. And it turns out that in this world of Weinstein domains, you can actually make this cell attachment, so you have a dk times d2n minus k, and you could make this cell attachment in such a way that you still keep the lambda, and so you still have a Weinstein domain after you attach the cell. So any Weinstein domain can be built by actually doing this handle attachment in a symplectic way. And so a subcritical handle means one whose dimension, where the core disk has dimension less than n, less than half the dimension of the space. Critical were the ones that had equal, their core disk equal to half the dimension of the space. Okay. So for example, I mean, you take any kind of one-jet bundle over a closed manifold, sort of a neighborhood of the zero section in that one-jet space would be an example of this. No, a one-jet space is no. I'd have to take a simplification of that. Yeah, I mean, the one-jet space itself is contact, but no. But no, I wanted to say something different. If I start with, no, I got this wrong. So if you start with an closed isotropic submanifold of, say, R2n or something like that, then a neighborhood of that in R2n would be an example of one of these subcritical Weinstein domains. That's what I wanted to say. So there are symplectic neighborhood theorems that tell you what such a neighborhood looks like, and it turns out to be one of these things. Okay, where am I? Right. So now, so far, we don't have any example where we know that symplectic homology is non-zero, so you might get the impression, right, that this is a really boring theory, but in fact, so my numbering is up to 3, I guess, so yeah. So number 4 is another theorem by Vilebro. So Vilebro proved that if you take symplectic homology of the cotangent disk bundle of a closed manifold Q with its canonical Liouville form, then, and then maybe here now I want to be slightly more precise. Let's take this with Z2 coefficients, and now I'm forgetting about, so I don't worry about orientations, I just count all my Floer cylinders mod 2. Then this is actually isomorphic to the homology, and I can even sort of be slightly more precise. So this is now shifted by n of the loop space of Q with Z2 coefficients. So that tells you that, at least for cotangent bundles, this is big, right? Because typically the loop space has infinite. I mean, on a closed manifold, the loop space always has sort of if I take the total homology of the free loop space, it's always infinite rank. All right. So if you want a statement like this now with Z coefficients, you have to be a little bit more careful. So then when you have to twist one of the two sides. Typically you would twist symplectic homology by a local coefficient system, and the local system that you would use comes from W2, so from the second Stiefel-Whitney class of Q by transgression to the loop space. So W2 assigns a number 0 or 1 to any two-dimensional surface inside Q. And so if I look at a loop in the loop space, that's like a loop of loops, so that's a torus in the base. So this local coefficient system assigns 1 to a loop in the loop space if the corresponding torus has W2 evaluated equal to 1 and 0 otherwise. And so we use twisted coefficients coming from W2 of Q. And then, so if you use these on one side of the two, then this becomes a true statement over Z. So this is due to Mohammed. And this is proved in very much detail in his, that was sort of the purpose of this thing, to prove that theorem. And in fact, once you get to a statement like this, and you're somebody like Somnath who knows about string topology, you might start to wonder, well, what about all these operations that you have on this side? Well, it turns out, I hope to get to that a little bit, you also have these operations on this side, and what Mohammed actually proved that this is an isomorphism of BV algebras. So, there's a product and there's a BV operator, and together they also generate a bracket, and so you have them on both sides, and this is an isomorphism respecting these structures. Okay. Right. And the last comment that I wanted to make in this remark section, yes? Yes. Yes. So you have this structure on both sides, and so it's an isomorphism of these structures. Yes, I mean, so string topology would be operations on the free, this is the free loop space, right? So string topology is operations on chains on the free loop space. So that's what I'm saying. So here on this side you would have the loop product and the loop bracket and the BV operator of string topology. So on this side, that's the operations are the string topology operations, and on this side they're sort of defined in terms of holomorphic curves. But then the point is, there's this isomorphism respects these definitions. Yes. All right. So the fifth remark is that another thing Viterbo proved if W0 embeds into W1, if this is a Liouville embedding, and I mean, maybe I didn't stress this enough yesterday, but all my Liouville embeddings are codimension 0. So these have the same dimension, right? So my pictures really sort of are, I have this subdomain W0 sitting inside this W1, and it sits in there sort of as a closure of an open set. And Liouville embedding meant, this meant that if I take the Liouville form here, then I can extend it to a primitive of the given symplectic form that I had on W1 in such a way that out here it's actually equal to my old Liouville form. So if this is the Liouville embedding, then we get a morphism, which goes the other way. So it goes from the symplectic homology of the big guy to the symplectic homology of the little guy. Okay. And so now, questions so far? I'm sorry? I think you can actually take your pick. You twist one of the two sides. So the point is, so there are examples. So I say if you take CP2 and you take the symplectic homology of CP2 with Z coefficients with the standard conventions, you would get 0. So then if you would have to twist the homology of the loop space to also get 0, or you would have to twist this guy to get something non-zero, so that you would get an isomorphism like that. So I think you can do both. Mohammed probably twists this side. Yes. Okay. So, yeah. It's just a morphism. So yeah, I'll get to that in a second. So for this to be useful, well, one thing I can say is that this morphism actually respects these other things I had. So I had these maps from the homology of W1 relative to W1 here, and I had the map from the homology of W0 relative to the boundary of W0, and I guess between those I would get a map this way also, right? Because just if I have a chain here relative to this thing, I restrict it to a chain relative to the bigger thing, right? So that's just so this would commute, and you can get some mileage out of that. But actually, I'm about to say something where this becomes much more useful. So let's talk a little bit about algebraic structures. So I have to be a little bit careful with time, but yeah. So I didn't have time to talk about it, but in general, whenever you have sort of Hamiltonian Floer theory, it comes with a product which is called the pair of pans product. Right? So what happens in a closed case is that you could really sort of get product just on a given Floer complex of a given Hamiltonian. Basically, so as a domain, before we used cylinders, right? And now what we're going to use is basically 3 punctured spheres, but I'm going to draw them like that. So I'm going to think of 2 inputs, 1 output. And basically, what you would do is you would sort of, in a closed setting, you would basically have Floer data on sort of these infinite cylinders near the ends, and then you would cut off your Hamiltonian. So in the interior here, it would just be a Hamiltonian holomorphic curve equation. So basically, you would study objects where here you have Floer data, here you have Floer data, and here you just have del bar, but no, so h will be 0 here. And you have the equation that you satisfy now depends on the point in your domain, and you study these spaces of maps, and this gives rise to, right? So this is why it's called pair of pans, because this looks like a pair of pans. So this would be in the closed case. In the symplectic homology case, you have to be a little bit more careful because again you have the slope conditions. So the way things work is that if you have slope A here and slope A1 and slope A2 here, then here you should put A1 plus A2 or anything that's bigger than that. So in order to get a well-defined theory, basically you have to sort of, the slope at the output has to be at least the sum of the slopes of the input. And once you do that, then, so you have products which don't sort of, which take elements now in different Floer homologies and land in a still different one, but then once you pass to the direct limit, sort of, passing to the direct limit, we actually find an associative product on symplectic homology. And this is also unital. The unit is basically given by counting sort of half planes like this with Floer data which is cut off appropriately. And now what's actually true is that this map, this morphism that you get from an embedding is actually now a unital ring map, which is much more interesting than just being a morphism of modules. I don't know who first observed this, maybe Mark McLean or maybe, I don't know. Do you know? I mean, yeah, so it's in the literature somewhere. I mean, it's certainly. Right, so a fact is that the Viterbo transfer, this is called the Viterbo transfer map. So the Viterbo transfer map is a morphism of unital rings. And so what that buys you, or maybe it's even Viterbo. I don't know. Yeah. I mean, he did lots of things, so let's just give him credit for this as well. So what does this buy you? Well, I mean, there are cases where you know, I mean, like for Cn, for example, we just proved the symplectic homology vanishes, so 0 equals 1 in this ring. And so therefore, if you have a unital ring map to anything else, then this anything else better also be 0. Right? So what that proves, one sort of corollary, which of course sort of was known before, but this is a nice proof of it. So, well, I mean, let me phrase it first in general. So, if W0 lambda 0 into W1 lambda 1 is a Liouville embedding, and the symplectic homology of the big guy is equal to 0, then the symplectic homology of the little guy is equal to 0. Because there's no unital ring map from the 0 ring to any non-zero ring. Right? Because here, if here 0 is equal to 1, this map sends 0 to 0 and 1 to 1, so then 0 has to be equal to 1 here too. And everything's dead. And so in particular, there are no exact Lagrangian submanifolds closed, I should say, exact Lagrangian submanifolds. Any Liouville domain with vanishing symplectic homology. Right, and so for Cn, this goes back to Gromov again, and now this is sort of a much more general statement. So this is now also true in any subcritical Weinstein domain or anything like that. So, yeah. So basically, the way you set this up is that for any values of A1 and A2, you get a map from the Floer homologies with slope A1 and the Floer homologies slope A2 into the Floer homology of slope at least A1 plus A2. And then you put together, you study sort of you have a whole bunch of collections sort of where A1 and A2 now range over the real numbers. And when you put them all together and pass through the direct limit, that gives you one product on the direct limit. So these are compatible with continuation maps in a suitable sense and so on, so that in the end, this gives you a well-defined product on the direct limit. So in principle, you have these for all admissible slopes, but then sort of as you pass through the direct limit, there's one product that survives, because they're sort of nicely compatible with all the continuation maps. Oh, this unit? Oh, so for the unit, well, I mean, you know from here, so the unit would typically come from the interior, right? So it would typically come not from the boundary, but sort of from things, from critical points in the interior. So it would typically be some maximum. So in the end, sort of this disk typically is a constant disk. The map. I mean, even though it's initially you define it to solve some holomorphic curve equation, but it turns out to be a constant map typically. Right. So, right. So what I wanted to explain was, well, yeah. Now I have 10 minutes for that, but. Here. So in fact now, what you can do is actually, so I already mentioned that the symplectic homology is a BV algebra. So in fact, slightly more is true. You can, well, depending on how ambitious you are, you could either take E2 or framed E2, and you get an action on the symplectic homology of that operad, right? So claim, and sort of the write-up of this is work in progress. With Kai, that symplectic homology of a Liouville domain has an action of frame D2. So in particular, once you pass to homology, that will give you this BV algebra structure. but there's more stuff to it. And in order to see why you would even expect this, and I don't really have time to explain any details, but just to get an idea of why you would expect something like this, and because it connects to many other talks that were given at this workshop, let me mention sort of what my model for E2 is. So we've had many talks on in this conference where the moduli space of genus 0 surfaces with some number of marked points appeared. So let me consider the case genus, right? So this is genus, and this is marked points. And I have n plus 1 of them, so I want to think of the one as sort of singled out as special as an output, and the other n as inputs, so n should be at least 2. And we know that if n is equal to 2, that this is just a point. Now, I want to do something slightly, so this is sort of, I have genus 0 surfaces with n plus 1 marked points, and I want to add one little piece of data, which is a tangent direction at the final marked point. So I'm going to decorate this by, I don't know, I think sharp hasn't been used yet. So this is just for the purpose of this talk notation. So M0 n plus 1 sharp now is genus 0 surfaces with n plus 1 marked points, and a marked direction, tangent direction, at the output. Right? So now M03 is no longer a point, but it's now a circle. So I said sort of I'm singling out this one special marked point. I'm calling it the output. The other ones I'm calling inputs. Yes. Yeah, so the marker would be something living in the projectivized tangent space, exactly. So it's just a direction. I don't care about the length, I just care about the direction. But the real projectivization, so yeah. So, yeah, because otherwise you don't get anything. And now, right, so, and now it turns out that if I compactify these spaces and I do a real compactification, so I really, so normally you would take sort of, if I didn't have this marker, I would take the Liouville compactification, so I would add strata of real codimension 2. And I would get a closed, actually, algebraic variety if you do it correctly. And that's not what I want to do. I want to compactify this this is the compactification which remembers the twist parameter at the nodes. So for each, whenever I have a nodal curve, I remember an anti-holomorphic identification of the tangent spaces. So it turns out that if I didn't have this marker initially, what I'm doing is I'm basically taking a real blow-up of this normal crossing divisor that I added in the Liouville compactification. But now, if I also take this marker, then I can actually, then it turns out that this, these spaces actually have a nice structure. So it turns out that the boundary of M0 n plus 1 sharp bar is the union over all splittings where I split this set 1 up to n in I union j, and then I have m length of I plus 1, 0 sharp cross m 0 length of j plus 1. So I get some relationship like that. So this is now really real codimension 1 boundary, and it's of this form. So you can see this. So I already told you M0 2 plus 1 sharp, that's the same as its compactification, and it's S1 because the underlying surface is fixed and I just have the marker. Now M0 3 plus 1 sharp. So now I have an additional marked point that can vary, so the underlying curve would be a punctured 3 punctured sphere, and now the compactification sort of adds boundary circles to this, and then we also have the marker, so it's this cross S1. And then we keep going, and you see that the boundary of this is 3 tori, and the 3 tori correspond to the 3 possible splittings of this into 2 subsets, which have... I'm doing something wrong here. There's something, yeah. One of them has an extra 1, because basically what this corresponds to is if I'm splitting. So if I have a nodal curve, then here is my output, right? So this is my output for this curve, and it has 2 inputs where one of the inputs actually is glued to the output of this curve. So my I in this case is this, right? So this is I, this is j, but then I have an extra input on this curve, which corresponds to the output of the other curve. So it turns out that this is a model of E2, and I'm going to use, the idea is now to use these things as domains for that parameterize. So now I have to add sort of Floer data and so on, so that I can write down Cauchy-Riemann type or Floer type equations with these domains, and then I can sort of the same way I did it here for the pans, and that's sort of the general idea that what you want to do. Now, to do this in practice is, so if you want to do it on this direct limit, it's just sort of really, really painful. So instead of doing it on a direct limit, you actually use a different model of symplectic homology, which is in some sense the analog of this Pearl complex that Sushmita talked about in the Lagrangian Floer homology case. Basically, what we do is we pick a Morse function on the interior of our Liouville domain, which has the boundary as a regular level set, and then we pick Morse functions on all the Rape orbits, and then we study actually holomorphic curves which are connected by gradient trajectories for these Morse functions. And then that's another model of symplectic homology, and in that model you can sort of implement operations coming from all these moduli spaces. And now whenever you have a chain here, that now gives you an operation on symplectic homology. So now maybe the last thing to point out is in this space you find 2 things that you've seen. Well, you find one thing that you've definitely seen a few times in this week, so I should mention this again. So now, in each of these spaces, you can look at a subspace where my n+1 points are all constrained on a circle, and they're in the correct order, so they start with the output and then 1, 2, 3, 4, up to n. And if I look at that compactification, that's actually nothing but another incarnation of the A-infinity Stashev operad. So that part of these moduli spaces, if I implement just that part, that gives me an A-infinity structure. And similarly, if I take the fundamental chains of all these things, then basically you could analyze that and you find that these fundamental chains give you an L-infinity structure. So those are sort of two substructures that naturally appear in E2, and then, but you have them all mixed up and you have all the compatibility conditions and so on. So once you have, maybe as a last remark, once you have that constructed, then what you can do is you can sort of extend this Viterbo transfer map, and you remove the assumption that the embedding should be Liouville. It could be any symplectic embedding. Now, sort of typically, you wouldn't have a map like that, but you have to sort of change the symplectic homology of the smaller one first. You have to, basically, the embedding gives you a Morav-Cartan element now in this L-infinity structure. You have to twist the boundary operator by that, and once you've done that, then you get a map. And that can be used to then get new results about non-embeddings of Lagrangians inside certain Liouville domains. So that's one of my goals, but I'm sorry, I didn't have time to explain that. And I really have to finish on time because we have to catch a car. So you still have a minute or two for questions. And then...
Any questions?
Yeah, sure. Yes, so on the sphere, there's no natural order, right? I mean, because on the sphere, order doesn't make sense. But once I constrain them on a circle, then order makes sense. I'm sorry?
At what point did you constrain them to be on the circle?
I just gave an example to say, as part of this structure, inside these moduli spaces, I have a hierarchy of chains which nicely sort of fit together, which correspond to all of them being constrained on the circle. And if I just look at that substructure of this full structure, then I will get an A-infinity algebra structure. So when I realize just that, and I forget about everything else, then I get an infinity structure, but I'm claiming I get actually more. I get this combined with all the other things that happen in this space.
Okay, so if not, let's thank Janko for a wonderful series of lectures.